In this second video of our two-part video series on LASSO modeling in tidy models, we're going to tune and finalize our LASSO model. Now recall from the previous video that we built 50 different LASSO models, one for each of 50 different possible values of our lambda tuning parameter. In this part, we're going to compare these 50 models and pick which lambda to use in our final LASSO. In terms of comparison, we'll focus on the cross-validated MAE, or the cross-validated prediction errors for each LASSO model. This information is stored behind our LASSO models object, the object where we stored our 50 LASSO models. And just as we did in least squares modeling, we can pull out information about the cross-validated metrics using collect metrics. This produces a table with 50 different rows. Each row corresponds to one of our 50 LASSO models. In the penalty column is the information about what lambda value was used to build that particular LASSO model. And the mean column indicates what was the cross-validated MAE for that model. So our first LASSO model, which used a lambda value of roughly 0.00001, on average, we anticipate that its predictions of height will be off by 1.78 inches. It's tough to look at this table of our 50 LASSO models and get any kind of meaningful comparisons here. And so to ease this process of model comparison, we will use visualizations. Specifically, for each of the 50 LASSO models, we want to plot the cross-validated MAE, or the prediction errors for that model, versus the lambda value used in that model. The built-in function that we can use for this plot is called autoplot, and we apply it again to our object where we stored our 50 LASSO models. Now I'm not going to pause very long here because I want to point out that on the x-axis, by default, it's not lambda that's plotted. On the x-axis, it's log lambda. And so to get this on the original scale, we can just add one more line of code. So to get our plot of the CVMAE for each of our 50 LASSO models versus lambda on the original scale, we add scale x continuous. So it's the same information on a different x-axis scale, but notice that the x-axis is labeled by amount of regularization. That means lambda. But just to remind ourselves of that and not lose track of what's on the x-axis, I'm going to explicitly put in lambda as my x-axis label. To this end, I can use xlab for the x-axis label. And there's a handy function in R called expression. It's pretty specialized, but when I apply expression to lambda, it will produce the Greek letter lambda, which we note on our x-axis here. Now the point of these videos is to focus on the R code, but I'll quickly point out what we're looking at here. In our plot, we have 50 different dots. Each dot represents a different LASSO model. The x-coordinate of the dot corresponds to the lambda value that we use for the tuning parameter behind that algorithm. And the y-coordinate corresponds to what was the cross-validated prediction error, or MAE, for that particular LASSO model. And so here we observe the Goldilocks effect. Mainly when lambda is very small, close to 0, the MAE, or prediction errors, are slightly worse. They improve as lambda increases, that is, as we regularize or simplify our models. And then when I go too far and increase lambda too much, then the prediction errors start getting worse and worse again. And so in our LASSO modeling, we don't get to use all 50 of these models. We have to pick just one. Right? A natural place to start is using the LASSO model with the lambda value that produced the smallest prediction errors. Now that lambda value is down here close to 0, right? But it's tough to visually pick out exactly what that lambda value was. And so we can use an R function. So this is our option 1. Pick a final lambda value, which produced the lasso with the lowest or best cross-validated MAE. The information about this lasso or lambda value is stored in our big lasso models object with all 50 of our models. To pick out the information about the lambda value that produced the best CVMAE, we can use the function select best. I want to select the best lambda with respect to the MAE metric. And I'm going to store this lambda information as best penalty. I'm just giving it a name in case I want to plug it into a model later. I don't have to track the actual number, I can store it. And so let's check that out. The best penalty or lambda value was roughly 0.013. And that tracks with what we observed in the plot. So going back up to the plot here, lambda of 0.013, yes, it appears that that minimized value of our prediction error happened at lambda around 0.013. Now, depending upon the context and the goal for our predictive modeling, maybe we don't want option 1. Maybe we don't want the lambda value that produces the best cross-validated MAE. Instead, consider option 2. Suppose that we want a larger lambda value that produces a simpler, more parsimonious model, but without significantly increasing the CVMAE. Again, we observed that as we increase lambda, the MAE increases, but we can find a lambda value that's larger and simpler, but doesn't significantly increase the CVMAE. More specifically, when I say doesn't significantly increase the CVMAE, we're going to look for the LASSO model whose CVMAE is within 1 standard error of the LASSO model with the lowest MAE. To this end, let's revisit our collect metrics. Again, each row here represents a single one of our 50 LASSO models. Which lambda penalty value it used, and what was the corresponding CVMAE stored in the mean column. Now, one thing I'll point out is that these CVMAEs are just approximations of this model's prediction errors. They're not perfect because we don't know exactly how our model will perform until we start applying it to new data. So these metrics are just estimates of prediction error. The column labeled STD error indicates the potential amount of error in that estimate. So examining this first row, it corresponds to my LASSO model that used a penalty parameter of lambda equals 0.00001. On average, we estimated that the prediction errors from this model will be off by 1.78 inches, again because we're predicting height. But we're not quite sure, so there is error involved in this estimate of error. All right, so we want to incorporate this error into our plot and our assessment of lambda. Again, we want to identify the lambda value that produces a LASSO model whose CVMAE is within 1 standard error of the LASSO model with the lowest MAE. To this end, we can start with our plot, these same 3 rows as before, or lines of code. All we're going to add to our plot are error bars. I do that with the function geom error bar. And these error bars are going to be drawn using information stored in our collect metrics table. Each of these error bars is going to be a vertical error bar. They're going to appear at each value of our lambda penalty term. That is, the x value at each error bar is going to be defined by that lambda penalty column. And then the bar is going to range from a minimum y value to a maximum y value. And again, I want to draw these at the CVMAE plus or minus 1 standard error. So the minimum or lower point of our error bar will be at our CVMAE stored as mean plus or minus 1 standard error stored as std_error. So the y min of my error bar is the mean, or MAE minus 1 standard error. And the maximum of the error bar is going to be at mean plus 1 standard error. And so notice I've added error bars to the estimates of prediction error for each of the 50 LASSO models. When we try to focus on the best lambda, the one that gave us the lowest MAE, notice that as I start cranking up lambda, making my model more simple, that the corresponding MAEs fall squarely within those error bars, meaning, yeah, my model's becoming more simple and the error's getting slightly worse, but not significantly worse. It's still within the error bars of the best MAE. And I can keep going, and when I get to a lambda value of around 0.2, that MAE, yes, is bigger than the best, but it's still within the error bars, meaning it's not significantly worse, and it's producing a more simple model. And if I crank up lambda to be bigger than that, then the MAEs start being outside the error bars, meaning significantly worse. So just visually, it seems that the biggest lambda, hence the simplest LASSO model that we can get, that has an error that's not significantly worse than the best, is at a lambda value of around 0.2. But again, it's tough to visually pinpoint that information. So we can pull it out using some R code. So we want to identify that lambda that produces our more parsimonious model. This information is also stored in LASSO models. And we pull it out not using select best, but select by 1 standard error. So we want to identify or select the lambda that produces the LASSO, whose MAE metric is within 1 standard error of the best. We also have to sort the information in the background, so sort the lambda values according or in descending order. That means we're focusing on the first in this order, which is the biggest lambda. So we want the biggest lambda possible, hence the most parsimonious model. So we stored that information to check out the results. The report is that we can use a lambda value of roughly 0.2. And again, that tracks with what we observed in our plot above. This lambda value of 0.2, its MAE is bigger than the best MAE, but it's still within 1 standard error. That is, it's not significantly worse. Okay, so we've now compared our 50 models. We've narrowed those 50 models down to 2. And just for the purposes of this video, I'm going to focus on the lambda value of my LASSO model that gave us the more parsimonious model. Okay, so let's finalize our model using this particular penalty parameter. In our final LASSO model, we start with our same LASSO workflow. This contains the information about the algorithm and the variable recipe that we want to apply to all of our LASSO models. But now I want to finalize this workflow. So instead of piping this into TuneGrid and again trying a bunch of lambda values over again, I want to finalize the workflow. And I want to finalize my LASSO workflow using this particular penalty parameter. Now that I have my general LASSO workflow, I know how I'm going to finalize that, or what lambda I'm going to use in my final model. I can use that information to fit my relationship of interest, which again was specified in my workflow, and I specified that I want to fit this relationship using the humans data. So to check it out, we can pull out our table of coefficients using the tidy function. And we get a coefficient table. We'll focus on the estimate column. The penalty column just indicates or reiterates what value of lambda we're using in this algorithm. And notice in our estimate column that a bunch of predictors have coefficients of 0. That is, the LASSO, the parsimonious LASSO, at least kicked them out. So just to focus on the predictors that remain in our model, I'll filter out and keep only the predictors whose estimates are non-zero. Exclamation point equals means not equal to 0. And notice that in our final LASSO model then, which is the most parsimonious model, we have 5 remaining predictors of the original 12 that we started with. Now this is our final LASSO model. We can go ahead and interpret and imply it as usual, and go communicate our model. But in one last step of this video, I'm going to zoom out and not just focus on this model, but on all 50 models again. Because stored in our final LASSO model is not only the coefficients for our final model, but also all 50 LASSO models that we looked at. So to get that output, or those coefficients for all 50 LASSO models, I apply 2 functions: extract fit parsnip and then pluck fit. What's happening here is that final LASSO model contains a bunch of nested objects. That is, objects within objects within objects within objects. And so to get this particular information about coefficients, I extract the nested objects that I want using extract fit parsnip. That pulls out each of the 50 model fits, and then from nested within each of those, I want to pluck specific information about the fit, or the coefficients. So what I want you to understand about this code is only that it's trying to get deep into this nested structure of the final LASSO model. So all LASSOs contains all of the coefficients for all 50 models, and finally we can plot all of those. Again, just looking at this plot alone is could be the subject of its own video. So I'll just point out what's happening on the axes here. On the x-axis, we have the range of log lambda values that we tried in our 50 LASSO models. On the top of the plot, we have numbers indicating how many predictors would remain in the model at each lambda value. And on the y-axis, we have the coefficients of our LASSO models. And those coefficients correspond to each predictor, and each predictor is represented by a line. So predictor 2 at the very top, we can observe that as lambda increases on the x-axis, the coefficient starts shrinking closer and closer and closer to 0. And eventually, it's kicked all the way to 0, and predictor 2 is kicked out of the model. This plot helps us understand, again, the phenomenon of shrinkage in the LASSO algorithm, the impact of lambda on our coefficients, as well as the number of predictors in our model, as well as what variables are more persistent than others. And if I want to narrow in and focus on specific predictors, such as, say, predictor 2 or predictor 8 up here, then I can get the information about which variables those are by listing out the row names of our all LASSO's coefficients. So variable 2 corresponds to weight, variable 8 corresponds to knee.